Welcome to UBBA Unplugged Live from the 2024 UBBA Summit Plugfest here in beautiful Kansas City, Missouri. I'm joined now by Dr. David Rieken of Hubbell. And Dr. Rieken, thank you for taking some time out of your day to be here.
My pleasure.
Excellent. Well, let's get a little hypothetical for this one, if you don't mind. If I gave you a magic wand and allowed you to essentially have high bandwidth access to every single meter, what would you do with it?
It's an interesting question. I think that's the purpose of this, really,
Right.
is to do that. Yeah, well, so the short answer is basically you would do everything. Any problem that utilities have on the distribution side right now can be solved by bringing back all of the data from the meter. And so the laboratory that I lead in Hubbell, it's Hubbell.R. It's an applied research laboratory. It's kind of unique in this industry to have an applied research laboratory, but we have it here basically because these kinds of problems are opening up right now. And we've introduced what I call the Hubbell smart meter conjecture. And the smart meter conjecture is basically, it's a little bit mathematical, but it goes like this. It's anything that happens on the distribution network can be seen by the meters. That is, anytime there's any kind of a voltage disruption or an outage, even anytime somebody turns on a switch anywhere on the network, there is a change in the signal that is seen across all of the meters on the network. So that is what we call the weak component to the smart meter conjecture. As a corollary to that, there's a strong component to the smart meter conjecture, which says that if everything that happens on the network can be seen by the meters, then you can figure out what's happened on the network by observing that set of signals in the network. And this is really what opens up the entire range of possibilities for us from the metering data. Now, so I'm going to tell you a story here.
Go for it.
I used to work in defense before I came here, and I worked at places like MIT Lincoln Laboratory. I worked at Phantom Works at Boeing. I did some work at General Dynamics, and my background is in radar arrays. I did my PhD defense on radar arrays for the E2C Hawkeye.
Oh, wow.
And so when I was doing DARPA-esque style work, and by the way, none of this will be anything that all of this is things I can tell you. That
Okay,
I did,
good.
Yeah. The problem that I was the most interested in is at that time UAVs were just becoming popular,
Right.
And so the Air Force and the Navy were looking at ways that they could put little radar sets onto all of these drones, and the idea would be you'd fly them around the battlefield and you could get little pictures of them. But what we were working on is if we could take all of the data from all of these UAVs that were flying around collectively and pierce them all together into one algorithm, you would actually have one giant radar array.
Right, and one big map.
And this is there's a well-known principle this is called array signal processing. There's a well-known principle in array signal processing that says that you actually get a better performing sensor by combining lots of tiny inexpensive sensors than you do by combining one. And in this case, the advantage to the Air Force and the Navy was those thousands or maybe hundreds of drones with their own antenna arrays on them were more powerful collectively than that one 747 with the giant flying
radar.
saucer on it behind it. Yeah.
Right.
And for a lot of reasons. One is if you shoot down one drone, you've still got the other 99.
Right.
The other one is really the drones are everywhere, and they're looking at it at every angle and every crevice, and there's really nowhere that you can hide from it, whereas you could hide from the others. So when I came here and I started working in the utility industry, I looked at the state of the distribution network and where all the sensors were. And at the time, we didn't call them sensors, we called them meters. But I thought this problem looks very, very similar mathematically to that problem in defense. In this case, replace the drones with the meters. And utilities are actually looking at this the way the Air Force and the Navy were 20 years ago, where they want to there was a big push to put giant expensive sensors on the network, PMUs, phaser measurement units, they called them. And these things are big and expensive, and they would be there just to solve that one specific problem. But they have the same deficiencies that the 747 with the radar dish on it had, which is basically it could only see a few things. It was very expensive. And so going back to the smart meter conjecture, we said, well, if every one of these meters can see everything, why don't we try doing the same thing that we were looking at there in the Department of Defense?
Sure.
Combine all these data from this meter and put it together and come up with what we could basically form a picture of what the network is. And the silver bullet for this, the single mathematical equation that makes this all possible, it's called state estimation. And if you every electrical engineering undergrad has to take a course in circuit analysis. It all comes down to Ohm's law. And in those classes, they give you a circuit and they say, if I tell you the voltage here is this and the voltage here is this, solve for the entire circuit. Well, we're looking at the same problem now with state estimation on distribution networks, except there the circuit is vast.
Yeah.
It's incredibly large, but the math is exactly the same. And what the meters do is they give you those numbers that your professor gave you for the circuit analysis. And so we just plug that into a computer, solve the equations, and then we can pinpoint everything on the network. Now this opens up then the possibility to figure out anywhere where there's power flowing, we can find that. And this means if there's reverse power flow, such as from solar panels, we can find that. If there are electric vehicles plugged in, we can tell you where they are and when. If there's somebody stealing power, that's unintentional power flow, we can find that. If there's high impedance faults, we can find that. And then once you can see how the network is behaving physically, then it's just a small step from that to say, well, you combine it with automation equipment, combine it with all your cat banks and voltage regulators and reclosers potentially, and you can start automatically manipulating those. Oh, yeah. And then you take that even a step further and you say, now if I can see what the network looks like here at this minute, at time t0, combine that with a little bit of predictive AI and say, what does the state of the network going to be in 5 minutes from now or 10 minutes from now? And then you can start automatically adjusting your equipment for what you expect to see rather than what you do see. At this point, you're not reacting to problems. Right. You're anticipating problems. And so we spend a lot of time talking about outage restoration and finding problems quickly and identifying them. At this point, we're getting into the ability to detect problems before they happen and stop them before they happen.
Right.
And that's where we really want to go. So that's the long answer to
Absolutely.
what you could do if you had this gigantic data pipe connected to every meter.
That's all. Well, all right, let's work on that. Let's get there, right? Because that's all incredible.
Yeah.
That's all incredible. Dr. Rieken, thank you for sharing that. Not only the story to put it into perspective, but just that incredible line of insight and where this industry could be going with the right systems in place. So thank you very much.
It's my pleasure. Thanks for having me.
Excellent. That's going to do it for this installment of UBBA Unplugged Live from the 2024 UBBA Summit Plugfest.